Thank you, Nathan. I would like to thank the organizers for inviting me to give a talk. And I also would like to thank Professor Greg Friedman, who encouraged me to go ahead with my talk, even though there were some last-minute fires, so to speak. And I will tell you all about this. I'm sure you're all excited to hear about this fibering theorem. But let me first ask you, can you see the screen that I'm sharing right now? No? Oh, no. Let me see, why has this happened? Okay, how about now? Okay, very good. Technical difficulties for a virtual conference can really, break the talk. So first of all, I'm going to start with a huge disclaimer. What I advertised as a fibering theorem, which really is a theorem that appeared in a paper which I published in the Journal of Groups Complexity and Cryptology. I believe actually has some more work to be done. Because as I was preparing for this very talk, as I was putting together the slides, one of my theorems kind of drew my attention, and I noticed that there is an oversight. So it's a gap in the proof, which no one likes to find out, especially not before a conference talk. And my initial instinct was to write to Professor Friedman and ask him to cancel my talk, but then I thought a little bit about this, and I decided that since there is a theorem, even though maybe not in the final form that I advertised, I could talk about that rather than cancel the talk altogether, because this result has proven sort of difficult for me to pin down, and I didn't want to cancel for the second time. So let me talk about this fibering theorem. There is a theorem there, even though it's not quite in the form that I stated in the slides. I will tell you what is different and how much it will change if I am not able to close the gap. If I'm able to close the gap, maybe I can still have it as published, but either way, I'll have to, write to the journal and the editors and see what I have to do about this. So fiberings of three manifolds. What are these? Well, we're interested in fiber bundles. So basically, we're interested in spaces which somehow sit as if they are sort of above the circle. So the topological language is basically, is this. So we have a continuous map from the three manifold to the circle. And if we look at the preimages of points in the circle, these are the fibers, and they're two manifolds. So why are we interested in things which fiber? So I wish I had, I'd been able to put together some sort of a picture, but I'm really not used to these virtual conferences, and I miss the blackboard. But sort of when one thinks of a fibering, at least when I think of fibering, the classical picture is of the torus being the fiber bundle over the circle with fibrous circle. So you can see, there's an obvious map, and each circle of the torus maps down to a single point down in the base space, which is the circle. So why are these things interesting? Well, we're talking about three manifolds, and if we want to be able to draw some wisdom from the world of surfaces, which was classically understood before three manifolds, we can build a three manifold from a surface by just taking some automorphism of the surface and then forming the mapping torus. And the mapping torus, this is simply, it's the space of the surface crossed with the interval. So you have kind of a thickening of the surface in 3 space. And then you end up gluing the 2 ends, but you don't necessarily identify points in the trivial way. So this is not necessarily, the surface crossed the circle, but you identify under some automorphism. And so this is called the mapping torus. So, given a surface, you can construct a 3 manifold this way. And in a certain sense, this is probably the simplest non-trivial manifold you can construct from a surface. There is also historical reasons why these these fiber bundles over the circle are important. And one of them is that hyperbolic structures in 3 manifolds were first discovered in fiber 3 manifolds. So this result is due to Thurston, and it is basically the hard part of the virtual fibering conjecture, I think. So the result that I'm alluding to is this: if M is a 3 manifold which fibers over the circle, and its monodromy is a pseudo-Nosov automorphism of the fiber, then M admits a hyperbolic metric of finite volume. And the special case of that theorem was proven when the fiber is a punctured torus, but again in the setting of manifolds which fiber over the circle. A more exotic result, which I really, I'm not going to do anything with this, I just thought it is a very interesting result, and it provides the motivation of why one wants to study fiber bundles, is this result, which is due to Cannon and Thurston. And I think it was proved sometime in the 80s, although I wasn't able to quite get, the year when the paper was published. So if we have a hyperbolic 3 manifold which fibers over the circle, and the fiber is some surface F, then we have, each fiber is included into the manifold. There is a standard embedding of each fiber, which lifts to a map from the universal cover of the fiber to the universal cover of M. And this map extends continuously to a map from the compactification of the universal cover. And so the surface is covered by the hyperbolic plane. Its compactification is the disk. So we have we have a map from the disk to the compactification of the 3 ball, sorry. And the boundary of the hyperbolic plane under this map is going to give space filling curve in the sphere at infinity of the hyperbolic 3 space. This was, I thought that was kind of an exotic result. I haven't looked at the proof. I have no idea, how they arrived at this. But for me, this was enough motivation to think that fibered manifolds are sort of special. So now I hope that this provides enough of motivation to study them. What sort of fibering theorems have been proven so far? Well, the classic is Stalling's fibration theorem. So for those of us who don't remember this, let me remind you what the setting is. So if in one direction, this is something from our algebraic geometry class, algebraic topology classes. That's a classical result. It's not trivial, but this is very well known. So whenever we have a fiber bundle, the E is the total space, and B is the base, and F is the fiber, which is the preimage under the projection, the bundle projection map of any point in the base. So a fiber bundle has the homotopy lifting property with respect to all CW pairs. And what this means in the language of homotopy groups is that we have this long exact sequence of homotopy groups. So we have a long exact sequence of pi n of the fiber and the and the total space and the base. And so what this means for us when we're looking at the three manifold is that, if you look at the relevant portion of it, you really have an exact sequence like this. So you have the fundamental group of the fiber, which injects into the fundamental group of the three manifold, which fibers over the circle. And you have a quotient, which is Z. So what is Stalling's fibration theorem? Well, knowing that this holds for any fiber bundle, for any three manifold which fibers over the circle, it's a natural question to ask, what happens if we have such an exact sequence? Does the manifold fiber? And Stallings actually was able to prove this in the affirmative, and the answer is yes, it does, but you need some extra hypothesis. So here is his fibration theorem. It appeared in a paper which was published in 1961. So we start with the compact, irreducible three manifold. If we have a surjective homomorphism onto Z, whose kernel is finitely generated and it's not of order 2. So this is important because of all sorts of technical problems. Then, in fact, we have the converse, M fibers over the circle with fiber a compact surface whose fundamental group is isomorphic to G. So in other words, we start with this short exact sequence, and Stallings proved that we end up with a fiber bundle. And what is more, we identify the kernel of the homomorphism onto Z with the fundamental group of the fiber, the surface, which is the fiber. Now, moving forward 10 years, I think about 10 years after Stallings proved his fibering theorem, there was an extension which Hempel and Jacob proved, and it essentially strengthens Stallings' result. So we have the following theorem due to Hempel and Jacob. It appeared in print in 1972. And the setting is this. Again, we start with a compact three manifold. And again, we're going to start with a short exact sequence, kind of, we're mimicking the situation of a fiber bundle, the portion of the long exact sequence of a fiber bundle, which is relevant for a three manifold. So if we have this, with the assumptions that N is finitely presented. So at that time, the requirement was, this was a more restrictive requirements than being finitely generated. So if the kernel of the homomorphism here is finitely presented, normal subgroup of the fundamental group of the manifold, and the quotient is infinite, and if further the kernel is not infinite cyclic and M doesn't contain a two-sided projective plane, then a certain manifold M hat, this is called the Poincaré associate, which is the connected sum of a manifold M1 and a homotopy three sphere, fibers. So this manifold fibers, and it's a fiber bundle over the circle with fiber a compact two manifold, so a compact surface. Or we have the case, it's the union of two twisted die bundles over a compact manifold, and they meet at the corresponding ends at the zero sphere bundles. But in either case, the kernel of the homomorphism onto this infinite group Q, the kernel N turns out to be a subgroup of finite index of the group carried by fiber of the fiber bundle, so the fundamental group of the fiber. And further, they conclude that the group Q onto which the homomorphism surjects is an extension of a finite group by either the infinite cyclic group in case 1 or the infinite dihedral group in case 2. So this seems like, there is some, we require more in this case than in Stalling's fibration theorem. However, there have been more results since then, which are relevant to this setting. So my PhD advisor, Peter Scott, proved that the fundamental groups of compact three manifolds are coherent. So that means that if they are finitely generated, they are finitely presented. And also he proved the existence of what's known as a compact core for a three manifold, and that is a compact submanifold which carries its fundamental group. So now if we look at the group N, this kernel of the homomorphism of Q here, it is the fundamental group of a compact three manifold. So we can take the cover of M, which corresponds to N. That may not be compact, but if it is, if we assume that N is finitely generated, then the core theorem of Peter Scott will prove that we have a compact manifold which carries that fundamental group. So therefore, we will conclude that N is finitely presented by his coherence theorem. And so therefore, in practice, in order to apply Hempel and Jacob's criterion, it suffices to assume that N is finitely generated, even though the theorem was stated in terms of finitely presented. And again, in that theorem, we are able to identify the kernel of the epimorphism with the fundamental group of the fiber of this fiber bundle. Another thing is that even though the theorem here had a statement about the Poincare associate, and one of the direct summands of the the statement really tells us something about one of the summands of the Poincare associate. It says that M1 fibers, and we have a connected sum with the homotopy 3-sphere. This theorem was proven before the geometrization conjecture and the proof of the Poincare conjecture were known. So now we know that there are no homotopy 3 spheres except for the honest 3-sphere, but that the honest 3-sphere is actually the identity for the operation of taking connected sum. So really what tells us is that the M fibers over the circle in the manner that this theorem shows us. Now, from fiber rings, we make an extra step forward, and we would like to ask the question: well, what results are there if we allow for a virtual fibering? In other words, maybe the manifold itself won't fiber, but some finite cover of it will. Well, there are lots of these. So in the case of hyperbolic manifolds, there is the virtual fibering theorem by Agel, Weiss, and others, which was proven in 2012. That is in a totally different direction from what I intend to go with this talk, but I didn't believe that I could proceed without mentioning it. So the theorem says that if M is a hyperbolic manifold and its fundamental group is virtually compact special, what that means is that pi1 of M is going to act in a co-compact manner on certain non-positively curved cube complex. Special simply means that this cube complex is such that the hyperplanes, satisfy certain technical conditions. So this was proven by Weiss. And then from this, it was concluded that pi1 is virtually quasi-convex subgroup of a right-angled Artin group that was proven by Haglund and Weiss. And then Agel finally proved that after all of this, M is virtually fibrous over the circle. So we have, and this is a major theorem. We have also this fibering result. So some more fibering results. So this is due to Agel. If M is aspherical and the fundamental group of M satisfies the residually finite rationally solvable condition, then M virtually fibers. And there is just another theorem that I'm mentioning just out of curiosity. If M is a closed three-manifold such that its product with the circle is a symplectic four-manifold, then M is fibered. I wasn't able to track down this paper. I found this in some work that Ian Agel had posted on his website. But nevertheless, I felt that this was interesting enough to mention. So the results that I actually want to talk about are more in the style of Stallings and Hempel-Jacob. So there is a theorem that was proved by one of my PhD advisor's PhD students and appeared in print in 1983. There is a theorem by Hassan.
Let me jump in real quick here. You've got just maybe 2 or 3 more minutes. So if you
can tell that I really I'm really not used to the format of the slides talk, but at any rate, so we have I'll probably be able to just state the result, which is just as well, because of what I mentioned is that I found a rather unpleasant gap, which is going to weaken some of the conclusions of my theorem. But maybe I'll be able to just get to that. So Elkawa proved that if M is a P2 irreducible compact and connected three-manifold, and its fundamental group contains a subnormal subgroup, which is contained in an indecomposable with respect to free product and finitely generated subgroup U of infinite index in G. And if G is U residually finite and the subnormal subgroup N is not infinite cyclic, then M is covered by a fiber bundle over S with fiber compact surface. So basically what this says is that after all of these technical conditions, M virtually fibers over the circle with fiber compact surface, and the surface group, the fundamental group of the fiber is commensurable with this bizarre subgroup U here. So subnormal, I assume that everyone knows this, but I will make the definition. Subnormal, N is subnormal if it's not quite normal in G, but there is a chain of normal subgroups, a composition series which starts at N and terminates in G. And a residual finiteness, I'll just omit this because I'm pressed for time, but that's another technical condition. There is a theorem in the same vein, which was proved by Moon, another student of a PhD student of Peter Scott, and he proved that if M is a compact three-manifold, if the fundamental group of M contains a finitely generated infinite index subgroup U, which contains a subnormal subgroup which is not infinite cyclic, then M is finitely covered by a bundle over S with fiber compact surface F, and the fundamental group of the fiber is commensurable with U. So this is a theorem, and the key words here are geometric. So I'll omit the second half of Moon, but I want to say a few words that, a manifold is geometric if it's basically modeled on one of the 8 three-dimensional geometries. Because I'm really pressed for time, I'm assuming I will just get to the point where I'm able to state my theorem. And here is what I was hoping I would be able to talk about today. So my strengthening is this. Moon proves fibering in the case when M is geometric. Well, he really proves it for torus sums, but I want to focus on the geometric part because this much remains true in my work, even though I found this horrible gap. So if M is an irreducible compact manifold with an empty or toroidal boundary, and its fundamental group contains a finitely generated subgroup U of infinite index in G, which contains a subnormal subgroup. And if N has composition series in which the terms, except possibly for the terminating term, the smallest subgroup, are all finitely generated, and if this subnormal subgroup intersects the fundamental groups of all the splitting tori, which are guaranteed to exist by the geometrization theorem, and if the intersections of this subnormal subgroup with the fundamental groups of the geometric pieces are not trivial and not infinite cyclic, then M has a finite cover, which is a bundle over S with fiber a compact surface. So this was a theorem, and I go on to say that we can even identify what the fundamental group of the fiber is, except that, as I said earlier this morning, I found an unfortunate mistake. So if I excise the part which is not true due to that, I still prove that the manifold fibers over the circle, but there is still more work to identify what the fundamental group of the fiber will be, and that it really will be commensurate with this subgroup U here. I realize that I've gone over time. I appreciate your patience, and I would like to ask if there is any questions at this point. I am afraid I went too fast over too much. I was perhaps too ambitious in how much one can do in 20 minutes.
I just put in the chat some reference of article related to that. Instead of exact sequence, Stolling's exact sequence for fundamental groups, you may consider such exact sequence of groups. And in that sense, you may deal not with fibering manifolds, but fibering orbifolds. And corresponding fibers will be not manifold, but orbifolds of corresponding dimension. So, and the reference I gave is for situation when you have such exact sequence when the group in consideration is finitely generated but geometrically infinite, or even not finitely presented group. So that way you may make several constructions on this way. Did you consider instead of manifolds orbifolds?
I have considered orbifolds, but in one dimension less, and partly because the motivating there is a theorem by Griffiths, which theorem motivated Moon to go ahead and prove his fibering result for 3 manifolds. So I've looked briefly at orbifolds which contain such subnormal subgroups, but these are 2-dimensional orbifolds. So I'm not surprised that there is a generalization out there in 3-dimensional orbifolds. But I wasn't aware of the existence of this paper, so I'll have to look at it and see what is in it. But thank you, Boris. Thank you so much for bringing this to my attention. I wasn't aware that there is such a result. I mean, maybe if we had more time, you could tell us more about what some of the
just take a look at this paper
Okay.
in Topology and Applications. You will see what can be done along this way.